And now Misha Pavel will be talking about the role of computational modeling in big data analytics.
Well, thank you very much for inviting me to present here. And let me set this up. Okay. I'm going to talk a little bit about a change of topics. I'm going to talk about behaviors and behavior informatics, and I will make a case for it. But I will spend a considerable proportion of the talk on thinking about what big data can tell us and how to deal with the problem issues of big data. So to motivate this approach, we look at data that tell us about how well people are doing in healthcare. And if you look at the effect of various factors on health, in this case, the effect on morbidity or mortality, there's a huge proportion of mortality, premature mortality, that's due to behaviors. In fact, if you think about things that we cannot do anything about, it's only 30% genetic that we can, at least at the moment, cannot do anything about. Everything else we can modify. And when you look at that 40% of premature mortality, it's due to behaviors. If we understood how to help people deal with behaviors and improve their health behaviors, we could tremendously improve not only the effectiveness of healthcare, not only the cost, but also the quality of life. And so that's why we in our group have been focused for many years on understanding behaviors and understanding how to use behaviors in healthcare and maybe helping people in changing them. Now, changing behavior is hard, and when we are continuously faced with this kind of dilemma, and almost always our impulse is to go to the left, I mean to the right, and we want to develop technology that will help people not to do that. Now, behavioral informatics is a new area that's that has to do with behavior monitoring, assessment, inference, and potentially intervention. And it's possible now because of the very good, very interesting advances in technology on sensor size, computation, communication, and even in behavioral sciences. This is just a view of what we see as mobile health, which is one of the frontiers of healthcare in general, and behavioral healthcare in particular. On the left, you'll see, at this point, we pictured a younger person, but that applies to all ages, that's being monitored at her own will. And of course, the privacy issues, I don't have to say, are very important and underlie a lot of what we're doing. And we are paying particular attention, even though I'm not going to mention much about it. Hopefully, my colleagues will solve that problem quickly. The mobile technology not only monitors, but also is used for intervention. And you can see the feedback loop going back to the user. And at this point, I want to just emphasize that the way we have been doing behavioral research in the past, when we ask people, what did you do last week, or even during the day, has been plagued with inaccuracies and all kinds of issues that have to do with context, randomness, etc. The new mobile health technology enables us to ask questions at the time that the person is going through in their life. So we call it ecological momentary assessment, and for that matter, ecological momentary intervention, when we can actually remind people in a context-dependent way, a context-aware way, so that, for example, we don't remind them to take medication when they are on the phone or when they are sleeping. So this is our vision of taking care of elders in the future. And at this point, I will say a little bit about privacy because it's going to come up. It's for the elders, it is a trade-off that it's comparison between cost and benefit. When you don't need care, you don't want to be necessarily monitored by others. But when that helps you remain in your home, if that helps you to remain healthy and safe, then you're willing to do quite a compromise privacy and privacy a lot. On the right side, we have all kinds of sensors, and I'm just listing some, showing some of a subset of those sensors. And on the left, we have a coaching platform and interventions in general, ranging from family to self-care to clinicians. Now, in order to achieve this, we need to have inference algorithm. We have to really understand what the data that we're collecting tell us. Now, the problem is that we need to do this in an unobtrusive way. The sensors that you see are almost never on the person, because we found over the last 10, 15 years that especially elders will not wear reliably, thanks more devices or sensors for more than like a week or two. And so all the sensors that we have been using are relatively unobtrusive. And the net result is that they are more sensitive to noise, they are more removed from what we want to measure. And so we need to develop these algorithms that will enable us to understand how behaviors convert to the sensors and sensor data. Now, I'm going to say more about that, quite a bit more about that in a second. The behavioral informatics is not just useful for healthcare, but also for economics, obviously, epidemiology, and especially for human-machine interactions. As we're building sophisticated robots to interact with people, we really have to understand the robot has to have some representation of the intentions or the behaviors of the person in order to build a robot that actually will safely interact with people. And there are some examples of folks doing that kind of work. Now, I give you a little bit of background. Big data, because we're monitoring continuously, is going to create huge amounts of data, and we already have examples of that, which I'll show you later. Now, that means we have to really understand about big data, and this, I would like to take a little bit detour and talk about the big data revolution. So, what is big data? Or I should say, what are big data? Well, it's probably, if you need to use Hadoop or MapReduce, that's big data. There's some misconception. I took this from my colleague at NSF, Tandy Warno, who used to be in charge of big data. If you cannot store it on your laptop, then it's big data. If you can store it there, it's not. And big data are just a lot of small data. Well, that's not correct. Really, big data are data that are not only about size, but also complexity, are data that current algorithms cannot handle. And that's what we considered, at least at NSF, as big data. The approach to big data requires new methodology, and that's what it's all about. what was disconcerting, and the reason I'm talking about it, is that I found this very disconcerting. There's been a number of publications. This is example of a very good, actually very good book, insightful book. But it makes statements like this. Big data marks an important step in humankind, quest to understand and quantify the world. But then it's very much opinionated about the fact that scientific methods and hypothesis-based research is not important anymore. And that, I'm going to show you, is very false. And it's not just one person who says that, like the editor of Wired magazine, but also others. In fact, in that book, they say society will no longer need to know why something happens, just that happens. Now, I wanted to show you, if we took this to the extreme, I hope the audio will work. No, it's plugged in.
For Howard Marks, I'm placing you under arrest for the future murder of Sarah Marks and Donald Dubin that was take place today, April 22nd, at 0800 hours and 4 minutes. No!
So this is a scene from a movie. This person was arrested for a crime that he will commit in 4 hours because our predictive algorithms told us that. So now the question is, does it work? And does it work without this knowledge of what's going on? So I'm going to go through very quickly through some examples of this kind of approach. So Google came up with a few years back, in fact 2009, published this nice paper about being able to predict outbreak of flu 14 days before CDC, and showed the wonderful results of that. And you would think, well, this is big data, this is the prototypical example of big data. They didn't have a model. Well, they did have actually a model, and it was very specific. It looked at the past queries, found the representation in terms of being able to optimize Bayesian prediction, and made the prediction, okay? Now, unfortunately, 2 years later, that failed. And so my point here is that the data that are based purely on black box prediction are very good for representing whatever is represented in the training set. But the generalizability of that is always questionable. Another example that's interesting, which I will show you requires model, is the recommending system that was originally developed by Amazon. And what they have is the people buying things and recommending them, saying they're rating them. And so they have a matrix of people by objects and the rating in that matrix. Now, natural approach would be, and they in fact tried it, is to say, well, if 2 people buy similar things, then they are similar. And if they are similar in most of things that they buy, we can predict from one person to the next. And I'm not going to bother you with the mathematics here, but essentially figure out how to do that. It didn't work. And the reason why it didn't work, and what did work, however, is when they look at similarity among items, not among people, okay? And that, so it's basically transposition of that matrix. This is very important insight because it tells us about the context dependency of human behavior relative to the object's behavior. Again, that required modeling. So there was just few examples that I was hoping to use to convince you that modeling is useful even if you have big data. In fact, I'm going to argue that every one of us is a modeler. If you ever computed an average, you had a model. In order for you to compute an average, you have to add numbers. And what allows you to do that? Why not multiply them or take a log and multiply them? Because you had some idea about the distribution that otherwise, maybe you never even thought about it, but you had it implicitly. And the point I'm trying to make, models, especially more complex, have to be made more explicit. So that brings us to the basis of measurement. What is measurement? Data are usually representation of some realities, results of measurements. So you have a phenomenon, and measurement is usually thought of as a map from objects to numbers. So, like such. And hopefully, you would be able to do with the numbers what you can do with the subjects, with the objects, but much easier. So you can put two masses together and you have sum of mass, but you can much easier add numbers. Now, however, usually when you measure, there is a contamination there is a transformation and noise added and so on. So in order to be able to actually make the inference from the numbers to the objects that you want to do, you need to have a model of the sensing mechanism. So even at the lowest level of sensing, you need to build models. And we often do it implicitly, but we need to do it explicitly. It's particularly important in social sciences because the transformations are more complex. So when you ask people to rate their pain on a scale from 1 to 5, you have to really understand what that person is doing, how she or he are using the numbers. And I'm going to skip this, but I want to just make point, as we saw yesterday in a very nice talk by Chua Wang, that you can take qualitative research and actually treat it as quantitative with slightly, of course, there are limitations of what you can do with discrete and set theoretic approaches than when you have numeric representation. When we go from and build models, we can characterize them on many dimensions. Here, I'm characterizing them on the basis of going from data-driven, where you know nothing about the phenomena that you're measuring, to principle-driven. So the example of a distribution is purely data-driven, or regression is very, very closely to data-driven. Or then Newton's laws would be very principle-based, and biomechanics is using those. So weaker models to stronger models as we add principled approaches to our modeling. And as we do that, we develop better and better predictive abilities. So to illustrate that, I'm going to show you some striking results that have been recently obtained. Note that folks that talk about big data without deep knowledge of it, they say, well, and for big data, you can take all the events or people or objects, and so you don't need to sample. Well, that's not true usually. Here is what recently came out, and this I got from Donna Kaufman. Purchasing diapers causes excessive drinking of beer. Why? Anybody can think of why this would be so? It turns out on Fridays, when you're getting ready for the weekend, you go and buy diapers, but also many people buy beer. And so a very strong correlation, and you can take all the people and you will find this correlation. Eating ice cream is a major cause of drowning. I guess you can figure that one out. And however, drinking soft drinks causes polio. Now that's a little more subtle, right? Well, it turns out polio used to be, when it was prevalent, it used to be, people got sick in the summer and was correlated. So what happens is that there is a latent variable that you cannot discover by just looking at correlations. And there are many techniques that you can use in order to introduce knowledge, and this is looking at factor analysis helps us as long as you can interpret the factors. Looking at structural equation modeling is helpful in that it's sort of like confirmatory factor analysis. Also, you can introduce assumptions and so on. I'm not going to go through those details, but I'm going to skip this because I'm running a little bit late. But I want to tell you about this one model that has been extremely successful. In fact, the most successful model, mathematical model that I know of, it's due to Ptolemy. He explained the movement of planets. And he developed a model in which he defined Earth as being very near to the center and the planets moving in these complex trajectories. The model had 47 parameters, but it accounted for a huge amount of data, a huge amount of experience. There wasn't that much data, but it was enough to actually do this quite precisely. Well, that model lasted 1,500 years. I wish my models would last 2 years. Then Copernicus came about and rediscovered the heliocentric system. But you know what? His predictions were not as good as Ptolemy's. Fewer parameters, but not as good as Ptolemy. He had circular trick, of course, that failed, so he couldn't predict as much. And the reason why Ptolemy lasted that long, it predicted everything that was necessary in those days. It could predict eclipse, and it could predict the position of planets. And then Tycho de Brahe actually constructed these tables of big data. This was huge data at those times of all the positions of the stars. And Kepler then figured out these laws that are represented in these represent these elliptic trajectories. Now this was an improvement, but it still didn't do as well as Ptolemy's. And but it was a much simpler model, and it explained a lot of things. Now it wasn't until Newton that we are able to now take an object, take a state of that object in terms of velocity and position, and predict wherever it's going to occur. So this is the main point. In order to be completely predictive, you need to incorporate as much as possible of principled approaches. And I just want to say that the few of the thinkers of the last century, have noted that theories are good things. But also Leonardo da Vinci, 500 years ago, said the same thing. Now, the last, how much time do I have? How much? Oh my God. So I would like to tell you a little bit about the home data that we are collecting and the big data that we are collecting. This is a typical apartment of an elder person, and outfitted with very simple sensors, like the motion detectors, few sensors modified by modifying field of view, and we have computer interactions, we have medication monitoring, and so on, door switches. And These are data actually from one person, and that was monitored over 1 year. Each circle is a day. I mean, each circle line is a day. This contains data from 1 year. The day starts in midnight, morning, 6 o'clock, noon. You can see that the first half a year, this person slept well, then it didn't. Then he didn't, or she didn't. This is bedroom, of course, the green. On every morning, she would make breakfast, lunch, and dinner in her home. But the interesting thing is, she didn't go out very much. She didn't socialize. This person, on the other hand, lives in a residential facility and would go and leave every meal and socialize down in a cafeteria. So you can see that this kind of visualization is an important way to think about data and understand your data. Now, I'm going to skip that, but this is basically a dynamic version of it, so you can fly through somebody's life. These data are actually looking at heart rate variability, determining stress of a person and recovery from stress over work days. As we go through the blue is the recovery time. I'm going to skip through this, only that this is one of the best visualization examples still. John Snow discovered the reason for or source of cholera in London by looking at where the cholera was people got sick, and then discovered that there was a pump. And once they closed the pump, the epidemics was contained. I'm going to skip this a little bit of science here. Here is a very simple example. Speed of walking is a very good indicator of your cognitive and physical well-being. And measuring speed of walking is often part of clinical tests. We have instrumented ceilings of hallways in people's homes, and we're able to measure speed of walking. But we really needed to build a fairly sophisticated model for these sensors in order to get unbiased measurements. But here is an example of one person, actually a real person. The speed of walking is the distribution is on the vertical axis, and the abscissa has the time, and this is monitored over like 3 years. And you can see that this person's speed of walking slowly declining. If we knew it here, we might have intervened. And in fact, at this point, this person was diagnosed with mild cognitive impairment. This person, on the other hand, has pretty steady walking speed, but got a stroke here. And we can actually watch the rehabilitation from the stroke in real life. And this is very important. You notice that something happened here, and we might have been, if we knew what we were looking for, we might have noticed that. And we're also looking at people's interactions, and even elders like to play computer games. We use those games to actually assess their health, cognitive health, their functionality, like for example memory or their attentional abilities, and using a simple model of the cognitive functionality, we can actually predict clinical tests from this and look at their evolution over time. So I just wanted to conclude by summarizing that the model-based approach is used everywhere from the sensors modeling, throughout the modeling of the processes of interest like behaviors, to prediction. And it's absolutely necessary in order to actually optimize intervention. And I, of course, didn't have time for that. So I'd like to end with this, and thank you for your attention.